Good morning. Welcome to another episode on linear algebra. Today we are going to state and prove what is popularly known as the dimension formula. Okay. And it goes by somebody's name, but I don't remember. But we will look at some examples and go ahead. Okay. So let me share the screen. Yes, this is the formula. So let us try to, before doing that, there is some unfinished business which I would like to talk about. You may recall when you talked about vector subspaces of R3, okay, we proved the following. The subspace are this, and then lines through origin, and then planes through origins, and then R3. So these are all the vector subspaces, okay. Essentially, we didn't prove these are all. For when it came to planes, what I proved is any plane through origin is a vector subspace, and we proved if suppose W is a vector subspace of R3, suppose dimension of W is 1, okay, then there is a non-zero vector V in W, and W has to be R times V. Why? Because this will be one dimensional, and W, okay, RV, okay, dimension of this will be 1, and RV is a this, but this dimension is also 1. Therefore, equality holds, right? Let's quickly recall why it happens. This is often used fact, which is left as an exercise in general. Let W is a vector subspace of V. Assume both are binary dimensional, dimension of W equal to dimension of V, then W is V. Because if W is a proper is not equal to V, it's a proper subset of V, okay, choose a vector V in V minus W, then choose a basis W1 to Wn, okay, where n is the dimension of V. This is the basis of W, okay. Then this W1 and V, this is linearly independent, right? Okay, I hope by now you should know how to do these things. Otherwise, I will be repeating, okay, what we did in the case of linear dependence, independence. It already motivates. V is not in the span of W1 to W1. Therefore, V must be linearly independent of W1 to W1. And W1 to W1 is already linearly independent. Therefore, this will be linearly independent. Anyway, check it, right? Therefore, I have an n plus 1 vectors, which is linearly independent in an n-dimensional vector space, W. But we have seen that if dimension of V is n, any, let us say x1 to xn plus 1, okay, give me any n plus 1 vectors, not necessarily distinct, then this will always be linearly dependent. So that's a contradiction because this is linearly independent, but this dimension of V is n, therefore it should be linearly dependent. This is a contradiction. So it follows that this cannot happen. Therefore, W must be equal to V. Now come back to this. Please pause, review, and then proceed. Because if this is the first time you are seeing, it's good to review this argument. And make sure you give this, okay? You should do this. Okay? Verify this. Okay. Now, therefore, if W is a vector subspace of R3 and dimension of W is 1, then W is some R times V for any non-zero vector V in W. Okay. And we have seen these vectors are lines passing through origin. These vector subspaces are lines through origin. This is what we have seen earlier in our lecture on vector subspaces. Now suppose dimension of W is 2. Then I claim W is a plane through origin. Okay, that's again easy. Suppose since dimension of W is 2, choose a basis, let us say x1, y1, z1 and x2, y2, z2. Okay, this is a basis of W, right? I want to say the W is given by an equation of the type ax plus by plus cz equal to 0. Okay, this is a plane. That means I have to find A, B, C. In particular, x1, y1, z1, x2, y2, z2 must be in this in W. That means it should satisfy the equation. Therefore, what are the unknowns? A, B, C. So I have to solve A x1 plus B y1 plus C z1 equal to 0. Ax2 plus by2 plus cz2 equal to 0. Now, what are known things? Notice that, okay, as usual, these are known. What is unknown? A, B, C. These are the unknowns. Okay. Now, how many equations are there? 2 equations. And how many unknowns? 3 unknowns. And what kind of equation? It's a homogeneous equation. Therefore, I can always solve for this. Okay. Therefore, there exists A, B, C, not all 0, 0, 0. That is a non-zero vector, so that these two equations are satisfied. Okay. Once it is satisfied, now start with any element in W. It's going to be a linear combination, but that you already know. Are you following what I'm saying? Because unfortunately, people just listen. They don't try to follow. So there exists A. Now I claim this W is nothing else than the set of x, y, z in R3, so that Ax plus By plus Ez is 0. Now what I know is x1, y1, z1 belong to this, x2, y2, z2 belong to this as well as to this. It belong to this, they belong to this. You understand this? Right. Okay. Now any vector in W, call it something like alpha, beta, gamma, which is in W, right? That is going to be a linear combination of x1, y1, z1 and x2, y2, z2. Since these are the solutions of this homogeneous equation, and this being a linear combination of these two solutions, it will also be a solution of the homogeneous system. You understand? And hence W equal to this plane through origin. Please pause, review, and then. Therefore, we have classified all vector subspace of R3 in a geometry, and we had understood their geometry. Okay. Okay. Now what we want to do, we are ready to prove the dimension formula. So let us look at the simplest, some other things. So fix a vector space over a field. It may even be infinite dimensional. Okay, it need not be finite dimensional, but anyway, whatever. Let W1 be a vector subspace of V and W2 is a vector subspace of V. Right? Then we want to define W1 plus W2 is a subset of V. Okay. How do we define? We start with x plus y, x is in W1 and y is in W2. Right? Add all such things. You follow that? Okay. We will look at immediately one example perhaps, so that it will be, you will understand what it is. Okay, an example. Let us look at the simplest example. Let me take R3 equal to V and my W1 to be R times E1, that is the x-axis. That is same as x0, 0, x in R. And now I know what I'm going to do. Can somebody tell me? Let us take E2, that is y-axis. That is 0, y, 0, y in R. Now what is W1 plus W2? Start anything in W1, that means x 0 0, where x is any real number. Okay, x 0 0, and take anything in W2, that is 0 y 0, where y is any real number. It should contain elements of this kind, where x is in R, y is also in R. Are there any restrictions on x and y? Nothing. They are arbitrary number. But what is this? This is x, y, 0. And what are x, y? X, y, no. So what is this? This is the xy plane given by z equal to 0. So now we are just now saying any plane passing through origin is a vector subspace. Therefore, what do I know? W1 plus W2 is also a vector subspace. This we already know. I'm just remarking. Okay. Is this example clear? Right? Okay. If you want to do something a little better, try to take the same VR3. W1 is the same, and let us say W3 equal to 0 YZ. Okay, Y and Z are real. Then what do you expect W1 plus W3 to be? Okay, just to do, if you want to understand, do this quickly. We will come back. Okay. Now what I want to claim is we are going back to the general case. W1, W2 are vector subspace of V. We already defined W1 plus W2. I claim W1 to W2 is a vector subspace. Okay, I could have written symbolically, since I've been using it all the time, you know this. Okay, I want to say this. What are the first? Notice that 0 has to be there. Why? Because 0 is in W1, because W1 is a vector subspace. Similarly, 0 belongs to W2. 0 plus 0 is 0. Therefore, that's correct. Next, take any two elements, x1 plus y1 and x2 plus y2. I hope the notation is clear. X1 is in W1, x2 is in W1, and y1 and y2 are in W2. Now, therefore, this is an element of W1 plus W2. This is also an element of W1 plus W2. So, I want to know whether it belongs to W1 plus W2. That's very clear, because I can use associativity, commutativity, etc., etc. Therefore, it's going to be x1 plus x2 plus y1 plus y2. This is some x, because x1 and x2 are in W1. W1 is a vector space, the vector subspace. Therefore, this will be x plus y. Therefore, it belongs to W1 plus W2. Okay. And similarly, t times. Suppose x plus y belong to W1 plus W2. Hereafter, whenever I write this, I will not explicitly mention the x is in W1, y is in W2. And I have to check whether t times, where t is a scalar. T times x plus y, whether it belongs to W1 plus W2. That's very clear, because of properties of vector space. This is t dot x plus t dot y, and x belongs to W1. W1 is a vector subspace. Therefore, this belongs to W1, and this belongs to W2. Therefore, this belongs to this. Okay. So we have shown that's the vector subspace. But now notice, okay, therefore W1 plus W2 is a vector subspace of V. Okay, this is done. Now, what is the relation between W1 plus W2? I'm sure all of you can say that, right? It is contained in this, because if you give me x in W1, then I can write x as x plus 0, where this 0 is, I can think of as an element in W2. This is an element in W1. Therefore, it belongs to W1 plus W2. And similarly, W2. So, W1 plus W2 is a vector subspace of V which contains W1 as well as W2. Is that correct? Okay. Next, I claim, can somebody prompt me? What should I claim now? Can somebody fill it here? Fill in the blanks here? Yes, it's the smallest vector subspace containing W1 plus W2. To prove that, what should I do? Let W be a vector subspace of V. Assume W1 and W2 are contained in W. Then what should I prove? I want to say this is the smallest vector subspace containing W1, W2. Therefore, what should I say? W1 plus W2 is contained in W. Okay, that's very clear. Why? Start with any vector x plus y in W1 plus W2. Now, since W1 is contained in W, x is in W. Okay, and y is also in W. But what do I know about W? W is a vector subspace. Therefore, x plus y must be in W. So, what I have shown? Any arbitrary element of W1 plus W2 is an element of W. Therefore, the claim follows. Okay, these are the two facts we have seen. Three facts about the sum. Okay, so we will say W1 plus W2 is the sum of two vector subspaces. W is the sum of vector sum of, if you want to say, sum of the vector subspaces W1 and W2. So what I have shown is this is a vector subspace containing W1 and W2, and it is the smallest vector subspace. Okay, please go through this, pause, review, and proceed. Okay. Before we go further, let's look at a very simple problem. Suppose W1 equal to W2 equal to W is a vector subspace of V. What do you think W1 plus W2 should be? Did I hear the answer correct? It should be nothing other than W, because any vector will be x plus y, but x and y are vectors in W, therefore that will also be in W. Right? Therefore this belongs to W. You understand? So all these two are equal. Okay, W1 plus W2 is contained in W. That's what I have shown. W1 plus W2 is contained in W. But remember, W1 is contained in W1 plus W2, but W1 equal to W. That means equality holds everywhere. You understand? Because it's set theory I have to prove. W1 plus W2 equal to W2. What I have shown is the W1 plus W2 is a subset of W. This is what I have proved. You understand? But I have to say they are equal. How do I do that? Because I can use this theorem, it's the smallest vector subspace, I can directly prove W1 is contained in W1 plus W2, but W1 is same as W, therefore W is contained in W. Yeah, therefore equality holds everywhere. Okay. I think that's more than enough. Let's try to prove the theorem. Okay. Now, before going to the proof, let's look at some examples. Suppose my V is R3 and my W1, let us say XY plane, and W2 is YZ plane. Right? So what is W1 plus W2? This is X, Y, 0 plus 0, some Y dash, Z dash, but that is equal to, this is a collection of all such things. This is X, Y plus Y dash and Z dash, and where X, Y, Y dash, Z dash are all arbitrary real numbers. But this is same as saying R3. Right? Because you give me anything alpha, beta, gamma, okay, I can take x equal to alpha. I want to write it as a sum of two vectors. That means I have to find x, y and y dash, z dash. These are the unknowns. This is given in R3. Can I write it as a sum of two vectors? One vector from W1, one vector from W2. That's what I'm answering. So if I take two vectors here, R and a vector in W1 plus W2, it is of this form. Okay, what are unknowns? X, y, y dash, z dash. So I can choose my x to be alpha and gamma to be z dash and beta to be any y. For example, I can take y equal to 0 and y dash equal to beta. Take y equal to 0 and y dash equal to beta. So you are through. You follow that? So that's no guarantee. That is, you can write it as alpha 0 0 plus 0 beta gamma. I hope that's the way I wrote it. It can be other way around also. Let me not worry about. Okay, that's it. Okay, right. Now, therefore, if I look at dimension of W1 equal to 2 and dimension of W2 is also equal to 2. Okay, now dimension of W1 plus W2 equal to 3 because it's R3. And what is W1 intersection W2? The points which must be common to XY plane as well as YZ plane. That means XY 0 and intersection 0. This means Z coordinate. If a point XYZ lies in W1, Z coordinate must be 0. If a point lies in the W2 plane, then the X coordinate must be 0. So if it lies in the intersection, then it should be X coordinate must be 0 and Z coordinate must be 0. That means it is Y axis. That is 0, Y, 0. Okay. And we already know this is a vector subspace. What is its dimension? Dimension of W1 intersection W2 is 1 because it's R times E2, where E2 is as usual 0, 1, 0. Right? So we have seen this. So more generally, start with any W1, okay, a plane through origin, and W2 also planes through origin. Then can you imagine if I take two planes through origin, either they may be coincident, suppose they are not coincident, okay, then what is their intersection? It will be a line passing through origin. Can you imagine that? Yeah. Therefore, okay, if W1 is not equal to W2, then W1 intersection W2 is a line through origin. Okay. And again, we will see the formula, dimension formula holds. What is the dimension formula? That is W1 plus W2 equals dimension of W1 plus dimension of W2 minus the dimension of W1 intersection W2. Okay. Just 1 second. Right? This is the formula we want to prove. Is it all right? Okay. Let us prove it. Before that, let's do some more exercises or some examples, because this theorem is very trivial. Just within 5 minutes, less than 5 minutes, one can dispose of this. But it's one of the most important results in linear algebra. There are two results where we talk about the dimensions, relating the dimensions of various subspaces. One is this dimension formula, the other one is rank nullity theorem. So whenever the numbers are involved, these two theorems will be of great use. Okay, so one should become more familiar and confident how to deal with this kind of stuff. Okay, so what did I want to say? I wanted to say that this one, okay, this is done. Next, let us try to say something more. I wanted to say something. Yeah, anyway, it's okay. Now let's look at some simple-minded example. Okay. I will assume this theorem. I am going to prove it in a minute. At present, let B equal to M2R, this is 2 by 2 matrices with entries in R, right? Now let us look at W1 equal to set of all A, B, C, A, where A, B, C are in R. Okay then. So it's easy to check this is the vector subspace of V. And let us take W2 to be 0, A, minus A and B, where A and B are in R. Again, this is easy to see that this is a vector subspace of V. Okay, verify this, verify this. That is a vector subspace. Okay, very trivial exercise. Okay, now I want to know what is W1 plus W2. Okay, of course I can try to work out, add everything. See, notice that since I used ABCA for W2, if you want, it should be arbitrary element, so you should maybe have to think of U minus U or B. That would have been better. You understand what I'm saying? You should not take ABCA and then 0A minus A minus B. You should take 0U minus UB, where U and B are arbitrary real numbers. Okay, I want to know this. We will do it in a minute, but let's look at what is W1 intersection W2. Now, what is dimension of V? That we had already seen, so dimension of V is 4. Now, what is dimension of W? W1? A, B, C, A. This is A. Therefore, how many variables are there? I need 3 variables. Therefore, all of you know, okay, from my lectures on dimension, okay, you know the dimension of W1 is 3. And what is dimension of W2? A and B, it needs only 2 coordinates. Therefore, the dimension of this must be 2. Right? Therefore, dimension of W1 plus W2 is 5. Right? Dimension of W1 plus dimension of W2 is 5. Right? But remember, W1 plus W2 is a vector subspace of M2R. Okay? And it contains W1. Therefore, this dimension should be dimension of W1 plus W2. See, now you can see some kind of analysis. It has to be greater than or equal to 3. Because this is a vector subspace containing W1. Dimension of W1 is already 3. And this is containing this, therefore it should be less than or equal to 4. You understand this? So I want to know what should be the dimension of W1 plus W2. Remember, I want to know what is W1 plus W2, but now I'm interested in dimension of W1 plus W2. Right? Are you with me? Okay. The way I want to arrive at it is very interesting. Let's look at W1 intersection W2. What does that mean? One vector in W1, any element is of the form AA, BC, and W2, any element is of the form 0, U minus UB. Right? What does it say? This object should be in W1 intersection W2. That means A must be 0, right? And B must be U, and C necessarily is minus U, and A is 0. Therefore, LA, this is consists of all elements of the form A must be 0, B must be U. Therefore, 0, U, minus U, 0. U varies over R. Are you following? Okay. Therefore, what is the dimension of W1 intersection W2? Okay, any element require only one coordinate, namely one real number. Right? For dimension of W1 plus W2 is 1. Now let's plug in the dimension formula. Dimension of W1 plus W2 equal to dimension of W1 plus dimension of W2 minus dimension of W1 intersection W2. This is 3 plus 2 minus 1, which is 4. Yeah. So what does it say? It says that W1 plus W2 is a vector subspace of V, but this dimension is 4, this dimension is also 4. Therefore, what we conclude? W1 plus W2 equal to V. Are you following me? So, okay. Now, what is the advantage? So, without trying to work out what should be W1 plus W2, that is equal to M2 of R, I concluded this by using only dimension formula. Whereas, what should I do? If you give me a vector in xy, M2R, let us say xy is a W, then I want to write it as W1 plus W2. That means it should be of the form 0, A, B, C and A plus 0, U minus U, V. That means I have to solve for x equal. This is going to be A, P plus U and C minus U and A plus B. That means I have to solve for x equal to A, y equal to B plus U and Z equal to C minus U and W equal to A plus B and solve for and do that. Okay, this can be done. Okay, this can be solved. Therefore, I can write any vector in M2R, that is any matrix in M2R as a sum of two vectors. Okay, to sum of two matrices, one in W1, another in W2. I can do this. In fact, I have done it, but it's a trivial exercise, so I don't want to spend time on that. You will be good, so you can do that. Okay, and again, I should like, okay, solve this. Solve this system of equations. Okay, so P R P. Okay, right. Now let's go through the proof of the theorem. I will come back to another example soon. So theorem proof. So what do we want to do? We want to relate to dimension of W1, W2 and W1 plus W2 and W1 intersection W2. Right? You want me to write? Okay, dimension of W1 plus W2 equal to dimension of W1 plus dimension of W2 minus dimension of W1 intersection W2. Okay, this is what I want to prove. So since it involves dimension, what does it mean? I have to count, I have to find basis for W1, W2, W1 intersection W2 and W1 plus W2. You understand this? Yeah, and then compute the numbers and prove this equation. Right? Yeah, but how do you think we will do? Once you understood this, okay, you have taken an important step in linear algebra. Whenever there is a subspace, and you remember W1 etc. W2 are subspace of W1 plus W2, and W1 intersection W2 is a subspace of these two, right? The trick in linear algebra is start with the smallest subspace and fix a basis for that, and then extend to a basis of the bigger spaces. You got me? You understood? Start with the basis of W1 intersection W2, extend to a base of W1 and extend to a base of W2. Then do something about W1 plus W2. That's all. Right? But before we go, usually I explain this, I forgot. This dimensional formula, does it remind you of something very basic counting principle? Suppose A and B are finite sets, then okay, I want to know what is the number of elements in the union. So this may be my A, okay, these are the elements, okay, and this may be my B, these are the elements, and these are the elements which are common to both. Then what do I do? Like when I count the number of elements, I will count these pink elements as well as the blue elements, and when I count the number of elements in B, I will count the number of green elements and the blue elements. Therefore, I count it twice. You understand? If I write mod A plus mod B, then these blue elements are counted twice. Therefore, what should I do? I should remove this. But what is that? That is A minus B. So it is minus A intersection B. Is that clear? You see that? That's a reminiscent of this formula. Okay, this is a digression, but it's very useful because many times teachers don't say that. It will be nice to know that. And in fact, that's all we are going to do. Okay, what we are going to do is we are going to find a basis for W1, W2 and extend to a base of W1. Are you following? Okay, dimension of W1 therefore will be dimension of W1 intersection W2 plus some extra elements. You understand this? You have doubt? Okay, let us come. Begin to think. Okay, that's very important. So let me start with let U1, U2, UK, okay, be a basis of W1 intersection W2. Therefore, what is the dimension of W1 intersection W2? That is K. Right? Now extend this to a basis of W1. So U1, UK are given. Let me call it V1 to Vm. So this is a basis for which one? W1. You understand? Similarly, extend this to a base of W2. So what do I get? U1 to UK union. Let us say W1 to Wn. This is a base of W2. You understood? Now how do I get a basis of W1 plus W2? Okay. Some guess. Any element of W1 plus W2 is X plus Y, where X is a linear combination of this, Y is a linear combination of these things. Therefore, X plus Y will be linear combination of U, V and W. Do you see that? Therefore, what should I expect? I should expect U1 to UK union, V1 to VM union, W1 to Wn. Okay, this is a basis for W1 plus W2. This is just our guess. There is no proof yet. Okay. Because suppose this is true, then I am through. Do you see that? What is my A? A will be this. Go back to the finite set. The dimension of W1 is number of elements in A. What is A? U1 to UK, V1 to VM. And dimension of W2 will be number of elements in B. What is B? V1 to VM. Sorry, U1 to UK. Yeah, maybe I should say that so that since I said something quickly, this is A. And what is B? B is and this is not included. Okay, that's B. Okay, this and this is B, and this and this is A. Right? Now you can see this principle, what I did. Okay, and A union B is this. So I want to claim it is a basis. Is that clear to all? Okay, first, so let us prove it. So the way I want to prove it, it is as first, the proof already was, we saw the trick was it should be, call this as B. I want to call B as a spanning set for W1 plus W2. Okay, that's first claim. That is clear because start with any Z in W1 plus W2. Then Z is of the form X plus Y. X is in W1, Y is in W2. But that is going to be some A1 U1 plus AK UK plus B1 V1 plus BM VM plus Y will be of the form B1 dash V1 plus BM dash Vm plus C1 W1 plus Cn W1. You understand this? Yeah, this is X and this is Y. Now what is this? This you can rewrite easily. This is going to be, let me just sum it up easily. AIXI, UI, I equal to 1 to K plus summation Bi, Bj plus Bj dash into Vj and J equal to 1 to M plus some other thing. Ct Wt T equal to 1 to N. Right? Therefore, any vector Z is spanned by U, V and W's. Therefore, one is proved. Pause, review, proceed. Next, I want to prove the set B is linearly independent. Okay. So what does that mean? Right? I will write as A1 U1 plus AK UK. Suppose this happens. B1 V1 plus BM VM plus C1 W1 plus C1 W1 equal to 0. Then what is that I have to prove? I have to prove all AIs, all Bs and all Cs are 0. Then that will follow, then B will be linearly independent. Right? I am fond of simplifying the notation, okay, because symbol have some meaning. So if I understand the meaning, I don't have to worry about the symbol. You understand? I will say you. I will simply write this as AU, and this I will write as BV, and I will write as CW. Is it okay? This is a symbol for me. AU stands for this sum, and BV stands for okay, and BV stands for this sum, and CV stands for CW stands for this sum. You understood that? Suppose this is equal to 0, right? Now I can write AAU plus BV equal to minus CW, therefore, right? Now, where is U and B? U and B, when I say U and B, that is U1 to UK, V1 to VM. Okay, don't forget. Okay, and this is scalar. Okay, this sum, where is that? AU plus BV is this sum. Okay, this sum. And where is this sum? This sum is in W1. Right? And where is this sum? This is in W2. Therefore, what does it mean? These are this element, this is a common element. This is belong to W1 intersection W2. Do you accept it? This is in W1. This is in W2. That means this element is in W1 as well as in W2. Therefore, it is in W1 intersection W2. Okay. In particular, minus CW. In particular, minus CW is in W1 intersection W2. What is minus CW? That is this element C1 W1 plus Cn W1 with minus sign. You understand that? Okay. But minus CW, that is, let me write it. Okay. But W1 plus W2 is the basis for that is U1 to UK. Therefore, this I should be able to write as W1 plus CKWK must be equal to sum alpha U1 plus alpha K UK. This is M. This is N, right? Yeah, N. Right? So bring everything to one side, then that means alpha U plus CW must be 0. I'm again using shorthand notation. I hope all of you are comfortable. Right? Now what do I know about U and B? That is U1 to UK, W1 to WK. Okay, this is the basis of what? Of W2. Therefore, that's linearly independent. That means my alpha is 0 and C's are 0. That is alpha is 0, Cj's are also 0. You understand that? Sure. So what I know is in the expression C1W1 plus CKWK, I proved all the C's are 0. Okay. Now go back. But what did I do? I said it is AU plus BB is CW. Now I know this is 0 vector. Okay, this is 0. Right? Again, AU stands for A1U1 plus AQUK and B1V1 plus BMVM. That is 0. But what do I know about U and V? This is the basis of what? Of W1. That means it's linearly independent. That means all my A's are 0 and all my B's are 0. Do you understand this proof? I am not writing A, B, J. Okay, you can do it on your own now. Okay, let us just do a PRP. Quick. If you don't like the shorthand notation, use A1, B1, etc. Check it. I already explained this proves it, but let's go through the proof. Therefore, B this is U1 to UK union B1 to BM union W1 to WK is a basis of W1 plus W2. Therefore, dimension of W1 plus W2 is K plus M plus N. You understand? Okay, but what is dimension of W1? Notice that this is a basis U1 to UK, V1 to VM. That is, therefore, it is K plus M. And what is dimension of W2? That is K plus N. This is N. You follow that? Notice that, as I said, this is your A, and A consists of these two, and B consists of this, and this consists of B. Right? So when I count, what do? I count this U1 to UK twice. So it has to be removed. But anyway, if you want only the pure algebraic way of formally doing, we are there. Therefore, dimension of W1 plus W2 is K plus M plus N equal to K plus M and plus K plus N minus dimension of W1 intersection W2, that is K. Okay, this is correct. So we have proved the result. Okay. Okay, I just checked I am recording. Sometimes I do forget. Okay, good. So the theorem is proved. As I said, this theorem is very important theorem. Whenever there is a dimension involved, we have to deal with it. We should know how to do that. Okay, right. Oh, I'm sharing. Okay. Now let's look at a final example. Okay, these are all very geometry example. Usually it's not done. Only computational exams are done, which I also have done something. Okay. Now suppose we have V equal to R3, and let's assume ABC is not 0. Right. Let's look at the plane defined by Ax plus By plus Cz equal to 0. We know dimension of W is 2. We know this is a vector subspace, the dimension is 2. Right? Okay. Now I want to claim if I take W plus, let us look at R times ABC. Notice that ABC is non-zero vector. Therefore, this will be one dimensional. Right? And this will be 2-dimensional. So I should expect this. Do I want to know whether it's 3-dimensional? Okay, dimension of this is 3. Yeah, yeah. Maybe I should do it in the next lecture when I deal with direct sum. But anyway, since now that I asked, okay, I so dimension of this will be equal to 3, provided ABC does not lie in W. Understand this? Because then ABC will be really independent of W. Therefore, one dimension will be added extra. Can it lie? Suppose it lies in W. What does that mean? That means in place of X, Y, Z, I have to substitute ABC. So if ABC lies in W, that means A times A, that is A squared plus B squared plus C squared equal to 0. That implies A equal to B equal to C equal to 0. That's a contradiction. Right? Therefore, this plus this, okay, W plus R times A, B, C should be R3. Yeah. I just wanted to do something before that. I totally forgot. Okay. Suppose in the theorem, okay, we looked at W1 intersection W2 and looked at basis U1 to UK. Suppose this is already 0. What do I do then? If I attended my existence of basis, you know that for 0 subspace, empty set is a basis. Either we proved it or we took it as an axiom, whatever you want, right? Therefore, are you following me? Yeah, because that case also I should understand. Because, all right, in that case, what do we do? Let us look at W1 to B, V1 to Vm, and W1 to Wn. This is the basis of W2, this is the basis of V1. Then this union is a basis of W1 plus W2. Right? Therefore, the dimension formula is still true. Are you following me? Because if you take x plus y, x is going to be summation ai vi I equal to 1 to m plus summation vj wj 1 to m. That's right. Okay, so it's a spanning set. Then if it is linearly independent, I have to prove. Okay, that I have to prove this is linearly independent. If okay, suppose this is equal to 0, that means as we argued earlier, ai vi must be equal to minus bj wj. This is in w1, this is in w2. Therefore, both are in w1 intersection w2. You understand? But that is 0. That means this vector must be 0. This vector must be 0. But remember, v1 to vm is basis of w1 linearly independent. Therefore, this sum equal to 0 implies all a's are 0. Similarly, all bj's are 0. Therefore, the proof is true. Okay, the theorem is true. a1n w1 intersection w2 is 0. Okay, I wanted to do that as a first case, but since I explained w1 intersection w2, the basis must be extended. I immediately started that. Okay, I hope all of you understood. Okay, there is one more exercise which I just gives as an exercise which I worked out, but that will be a little too boring to write all those things here. Lot of computation. So let W1 be the linear span of these two vectors 1, 0, 1 and 1, 2, 2. Notice this dimension of W1 equal to 2. Why? None can be linear scalar multiply of the other. Therefore, these two vectors are linear independent. And let W2 also be the linear span of 0, 1, 1 and minus 1, 0, 2. Again, these two vectors are linearly independent, therefore dimension of W2 is also 2. Right? Therefore, I should expect W1 intersection W2 dimension of this must be 1. Are you following why I'm saying that? Okay. right? So because this their dimensions will add up to 4, dimension of W1 plus W2. Okay, and dimension of W1 plus W2. Notice that W1 is contained in this. W2 is also contained, right? And again notice that this vector cannot be a linear combination of these two vectors, because if it has to be, then A times 101 will be A, and here B times 122 will be B. Therefore, A plus B equal to 0. You understand that? That means A and B are different. But then A times 0 will be 0 and B times 2 you want. Are you following me? 0, 1, 1. Okay, linearly independent of 101 and 121. 122. Because if 0, 1, 1 is A times 101 plus B times 122. I hope I am writing it correctly. Yeah, that means this must be A plus B, and this is 2B and A plus 2B. You understand this? Very good. So A plus B must be 0. That means A equal to minus B. You follow that? Okay. Now let us look at, that is A plus B is 0. Now this says 2B equal to 1. This and this 2B equal to 1. And this says A plus 2B equal to 1. But 2B is already 1 and A is minus B. You understand that? A is minus B plus 2B, that is equal to 1. B equal to 1. But already 2B equal to 1 and B equal to 1. This is a contradiction. Therefore, it's not linear. Now, these three vectors 101, 122 and 011 must be in the vector subspace W1 plus W2. Therefore, these three vectors 011, 101 and 122 must be in W1 plus W2. But these are three vectors linearly independent. Therefore, this dimension, okay, dimension of W1 plus W2 must at least be 3, but that's a subset of R3. Therefore, subspace of R3. Therefore, its dimension at most is R3. Therefore, W1 intersection W2 dimension must be equal to 1, right? Therefore, it should be of the form R times some vector. Question is, identify this vector. See, this vector is not unique. Any scalar multiple. So I identify such a vector. That is the exercise. I have found one, but it has 1, 6, 4. Okay. Or say a scalar multiple, non-zero scalar multiple, just to verify. Okay. I hope you enjoyed this lecture. As you can see, the theorem is very, very simple. Less than 5 minutes, one can work out. But you see that I gave a variety of geometric ideas and examples, computational and theoretical, both included, so that you can appreciate. I hope all of you enjoyed. Have a good day. Take care. And this more or less finishes whatever I wanted to say about the chapter on vector spaces. We define vector space and the properties, and then we define vector subspaces, linear dependent independence, and basis, characterization, that is equivalent definitions. And then we also proved we computed a lot of examples of basis. Then we proved the existence of basis. Okay, then we computed the dimension formula and examples. This is the first chapter of one chapter of my book. Okay, and we had completed. There is an optional video which I will follow this, which just because of whatever we observed today, there is an immediate related notion of direct sum of vector subspaces, but that is optional. That is not necessary for second year BSc student. But if you hope to go for higher studies, it will be a very good idea. Okay, because we will give a lot of good examples also, and a much better understanding of the concepts is very needed. Okay, we will meet again. Take care. Bye.